Welcome to the problem-solving session for Chapter 30. Let's begin with question 1. Here, we are given a conductor in the shape of a square loop. Each side has a length 0.4 meters and carries a current of 10 amps. We are asked to calculate the magnetic field at the center of the square. Well, let's see. What we can do is that we can approximate each length of the side to try to determine the magnetic field that side contributes at the center of the square. So here's the center of the square. And what we see here is that if we start from the left end of the bottom, here is our ds, here is our r hat, this is our distance r, and we know that A is L over 2, or 0.4 divided by 2, but so is the base of the triangle. This is L over 2. And what we're going to do is that we are going to let this side coincide with the x-axis. So what we can do is to have a finite wire of length L, 0.4, and we set this up pretty much the way we set up the problem when we solved it in the lecture, and that is to make this our origin right here, and this will be a minus x here, and we have to get an angle theta, and then of course our dx here will have an angle theta. This is our r hat, and so we'll have an angle theta, which will be what we determine here for theta final. So again, this is our triangle here. So let's begin. If we consider this triangle with sides L over 2, L over 2, our theta initial is 45 degrees. That's a triangle with two sides that are equal. And this triangle here, although this angle will be 45, the inner angle, we want the outer angle, so we add 90 degrees. That takes us to 135 degrees. So this will be the end points. And if we recall, the expression for the magnitude of the magnetic field is mu naught I over 4 pi a, and then we have the integral of sine theta d theta, where our endpoints are theta initial and theta final. And of course the integral of sine theta d theta is equal to minus cosine theta, and we'll evaluate it at the endpoints. In this case, we can use pi over 4 or 45 degrees because we don't have to work with radians, so I can write the endpoints as 45 and 135. And let's see, come over here and substitute the values for mu naught, 4 pi e to the minus 7. I is 10 amps, 4 pi in the denominator times A is of course 0.2 amps, I'm sorry, 0.2 meters, because it's L over 2. And we come over here, we have minus cosine of 135 degrees, because we have minus cosine of theta final, minus cosine of 45 degrees, which gives us cosine of 45 degrees. And this is equal to square root of 2 over 2. This is equal to square root of 2 over 2. And when we add them up, we end up with a square root of 2 multiplying this expression right here. And when we multiply these terms out, we get 7.07 e to the minus 6 Tesla. Now that's the magnitude of B. Let's go ahead and see if we can get a direction for B. If you consider here that ds is along the I hat direction, r hat has two components, an I hat, which does not determine the direction for us, but the j hat does, so I hat cross j hat is k hat, and so the contribution of the bottom side is along the k hat direction. Now when we come back over here, if we consider now this end of the loop, the square loop, we get a contribution there that has the same magnitude as what we just calculated. And this time, if this is our ds, is in the j hat direction, so there's our ds. And if we consider that the r hat is going to have both the j hat, which we don't want, and an I hat component, in fact it's going to be negative I hat. So this is our, for example, if we started here so that we could see it a little better, this is our ds, and here is our r hat, which has a negative I hat component, so j hat cross negative I hat still gives us a positive k hat. And then if we consider the top, we also get k hat. If we consider the left end, we also get k hat. The long and the short of it is that the net magnetic field will be 4 times the magnitude of each individual, which was the same, 7.07 e to the minus 6 Tesla. And furthermore, because all of the sides contribute in the k hat direction, then we just add them all up, in other words, multiply by 4, to get a value of 2.83 e to the minus 5 Tesla, let's put our unit here, in the k hat direction. So in this example here, because we were dealing with a square, the distance from the center to each side of the wire was exactly the same, so all our values of A were 0.2 meters, all our values of I were 10 amps, and for each side we could define these angles here, the theta initial and the theta final, so that we would still get the same square root of 2 over 2 plus square root of 2 over 2 terms. Next question. Here we're asked to determine the magnitude and the direction of the magnetic field at a point 1 meter above and below a very thin, long power line. So here's our power line. It's very long compared with 1 meter. For example, so here's 1 meter, here's 1 meter. And we're asked to determine the magnetic field at these two locations, given that the current, I, is pointing due west, which for us is to the left. Now, if we use the right-hand rule, what we find is that we have a current that in this case points in the negative I hat direction. Our R hat points in the positive I hat direction, and so what we get is a magnetic field above that points in the minus k hat direction and below in the positive k hat direction. Because this is a very long line, we have from the Biot-Savart law, mu naught I over 4 pi times A, but when we take the integral of sine theta d theta, Our theta initial is 0, our theta final is pi, which means that the value here will equal 2, and this 2 will cancel 2 of these, and so the expression for determining the magnitude of the magnetic field is going to be mu naught I over 2 pi A. So when we are looking at the value of the magnetic field above the power line, we recall that that's in the minus k hat direction. We substitute all our numbers, 4 pi e to the minus 7 times 100 amps divided by 2 pi times 1 meter. This pi cancels this pi, this 2 cancels 2 of those, and we were in the negative k hat direction. So at the top, the value of B is equal to minus 2 e to the minus 5 Tesla k hat. The negative here is, of course, for minus k hat. At the bottom, the magnitude is the same because we're still considering 1 meter below, but this time our k hat is positive, so plus 2 e to the minus 5 Tesla in the k hat direction. Next question. Here, we consider a conductor which has essentially 1, 2, 3, 4, 5 parts. 3 of the parts are straight and 2 of them are curved, making an angle of 60 degrees with the point P where we're trying to determine the magnetic field. Now the outer arc defines a radius or a distance to the center which is 6 centimeters. The inner arc defines a distance of 3 centimeters. The current through each segment is 5 amps. So we come over here and we consider that we're trying to get the magnetic field at the point P, and we begin with ds for this straight segment pointing in the positive I hat direction, but R hat also points in the positive x direction, and so I hat cross I hat is 0, no contribution there. Here we have ds along the arc, and R hat points towards the center, defining a 90-degree angle, so we will get a contribution here. And if we use the right-hand rule, what we find is that from the outer arc, we get a magnetic field contribution at the point P, this is from the outer arc, which is in the minus k hat direction. And from this straight segment, we have ds along here, R hat along here, and once again, because they're both parallel to each other, the angle theta is 0, well, the sign of 0 is 0. So now we come back over here, we've got our ds along the direction of the current, R hat makes a 90-degree angle, and when we use the right-hand rule, so this was for the outer arc, minus k hat, for the inner arc, we get a contribution of positive k hat. And then lastly here we have ds, and R hat is towards P. Notice that the angle between ds and R hat is 180. The sign of 180 is 0, so we get no contribution from there. So now let's go ahead and use the expression that we derived for the magnitude. First of all, the magnitude here is mu naught I over 4 pi R being the radius of the arc, times theta in radian. So let's go for the outer arc. So in other words, when capital R is equal to B, we get B equals, and I'll write this as a vector. This time we'll include the direction, mu naught I over 4 pi times B. Theta radian is pi over 3, and the direction is minus k hat. For R equals A, the inner, we have B, so let's call this big BB and BA, mu naught I over 4 pi A, pi over 3, and remember we have to work in radian, plus k hat. So let's add these both up to get the total value of the magnetic field. We factor out mu naught I over 4 pi times pi over 3 equals, and this time we're going to use the minus k hat here to write this as minus 1 over B, the plus k hat here to write plus 1 over A, and of course the k hat is here. Clean this up a little bit. This pi cancels that pi. We're going to have, now the 3 here will multiply times 4. We'll end up with a 12 in the denominator. Let's substitute our numbers. 4 pi e to the minus 7 times 5 amps divided by 12 times minus 1 over 0.06 for 6 centimeters plus 1 over 0.03 for the 3 centimeters times k hat. And when we plug these numbers into our calculator, we get 8.73 e to the minus 6 Tesla in the positive k hat direction, and that is the net value of the magnetic field. Next question. Here we're given a solenoid which we're told is 0.2 meters long, and we're also told that there are 20,000 turns per meter for this particular solenoid. So they've actually given us little n. Now, then we're told that the solenoid is cooled below its critical temperature to become a superconductor. Well, why they're telling us this is simply to be able to tell us why it carries such a large current, which is 30 amps. So that's the current through the solenoid, which is very large. We've got little n, and we're asked to determine B, the magnitude of B, at the center of the solenoid. Well, if you recall from lecture, we calculated as mu naught little n times I, and this is a very easy problem then for pi e to the minus 7 times 20 e to the 3 turns per meter times I, 30 amps, and we get a value of the magnitude of the magnetic field at 0.754 Tesla. Well, this concludes the first part of the problem-solving session for Chapter 30. Until next time.